Our next speaker, our keynote speaker, I'm very happy that Bob Ham was able to join us today. Bob is one of the recognized experts in industrial accelerators. He has, well, maybe you'll tell us how many companies you have either owned or been involved with in your career. So he is in the accelerator business and has worked in a wide range of applications. He's called on by the Department of Energy to provide advice. He participated in the Accelerators for America's Future workshop. I know he's given presentations to the High Energy Physics Advisory Panel and other bodies within the Department of Energy system anyway that request advice on applications of accelerators. And I was thrilled when I sent him an email asking if he would be the keynote speaker. He said yes. And he said this may be one of his last presentations on this topic, maybe before retiring from this line of business. So anyway, we're thrilled that Bob was able to join us.
Thank you, Stuart. Glad to be here. Almost didn't make it, but glad to be here. I got in at 2 o'clock this morning. So anyway, as Stuart said, I'm Robert Ham. R&M Technical Enterprises is a consulting company that we have now, but I've been in this business for a while. So what Stuart asked me as a favor to come talk about was the industrial accelerators. So what I'm going to do in this talk, and try to go through it quickly, is talk only about the industrial applications of accelerators, excluding the medical and discovery science, which is the DOE's word for research machines, the big ones. But the industrial machines is now, it's approaching 2/3 of all machines that are sold annually. I've been talking about this topic since I gave a talk in Albuquerque at the Accelerator Applications meeting in 1997, and there's where I coined the commercial accelerator field as the beam business. And so this is what I'll concentrate on, the beam business. And these machines, I need to give a couple caveats. These machines include all what I call commercial. In other words, they're built by a company, not built by research laboratories. Commercial particle accelerators, except those generating internal beams. In other words, when I talk about the beam business, I don't cover CRTs, X-ray tubes, RF tubes, and any of the things that use accelerated charged particles, but internally to the device. I will talk about the present applications of these, the present status of these applications, and say a little bit about the future applications and the future technology. And it's always difficult to follow Stuart because he does such an elegant job of this, but I'll do my best. A couple of caveats as I go through the data, and what I'm going to do is start out with the whole beam business. And I want to tell you that the sales estimates of machines that have been sold and machines that are still working. So if you use them, you're assuming I'm correct. And I've worked hard on trying to do this and get all this data from publications. And actually, over the years since we did the book in 2010, I've been working with a lot of the vendors to try to make sure I had correct numbers. As far as future applications, I don't have a crystal ball. But as Stuart said, I do have 50 years of experience in developing accelerators, and 37 of those have been in 4 different commercial companies. So I've been in this commercial business for most of my career. I'll start out with an introduction by Walter Henning and Charles Shank from that workshop that Accelerators for America's Future. And it gives sort of the scope of this, and I'll let you read it, but a beam of the right particles with the right energy at the right intensity can shrink a tumor, produce cleaner energy, spot suspicious cargo, make a better radio tower, clean up dirty drinking water, map a protein, steady a nuclear explosion, design a new drug, make a heat-resistant automotive cable, diagnose a disease, reduce nuclear waste, detect arc forgery, implant ions in semiconductors, prospect for oil, date an archaeological find, package a Thanksgiving turkey, or discover the secrets of the universe. So that's the way of just telling you what we're trying to cover today is a huge field. A lot of applications, a lot of machines, and I'll go through that next. Here's what I'm talking about in terms of the commercial applications, commercial accelerator business, what I call the beam business. And Stuart's got some numbers that are a few years old, and for the article that we did in the Reviews of Accelerator Science and Technology, Volume 10, which is incidentally the last one, I updated these numbers. And as of 1 year ago, my estimate was that to date, 47,000 commercial systems have been built. Commercial accelerators have been built, and probably somewhere around 40,000 of them are still in operation. And you'll see what I'm talking about. Right now, there are more than 100 vendors worldwide in the accelerator business, primarily in the US, Europe, and Japan, but they're growing in countries like China, Russia, and India. And one can see that ion implantation, medical machines, and electron beam processing dominate the commercial business right now. We'll talk a little bit about the others and talk about the fields that are growing. In fact, you can see here's the vendors in each one of the fields of the beam business. So we've got e-beam welders, material radiators, ion implantation, etc. And the total is 116, and if you count these by the countries, there's somewhere around 100, because some of the vendors are in multiple applications. So this is just what complicates the field. So, but there are a lot of people, and in fact, what I've found in the past year since I put this data together for the RAST article, I found a number of more vendors that are in the field. So it's growing. And how fast is the business growing? Well, for the RAS 10, Dr. Doyle at Sandia Lab put together this slide that shows the growth from 2008, which is just before our book, to 2018 in different fields in terms of the annual growth. And one sees that neutron generators are not growing so big right now, but all of these fields are growing 2 to 9%. That's annually. So the average is somewhere around 4%. So this field is growing very rapidly. And this is how rapidly it's grown over the years. This is by all of the fields, including the medical, is the growth since 1968 of all of this equipment. And this actually has in it Discovery Science Accelerators, and you can see this gray line down here stays almost constant. So there's not a lot of those machines, but they're very important because that's where all this stuff was born. And then you see that the total of ion implantation and medical accelerators, which you saw from the pie chart, are about the same. And so this is the total of all of the industrial categories, and this is the total of all the accelerators. And you see that as of 2017, the projected total was, and I would say that these numbers are probably within a few percent. They're not, I can't say that definitely they're absolutely correct numbers, but it gives you the general trend. And one sees that there is no topping of this. It's in its growth phase right now in terms of the phases of the business. So I'll say just a word about the Discovery Science machines. Stuart elegantly covered all these different machines, and these are large systems. It's still a very active business, the construction of these. They require industrial input for building of things, but they're only a small part of what I call the beam business, commercial companies doing things. This was Dr. Mueller in the IPAC meeting last year came up with the projects that are underway over the next 5 years, and they came up with 275 million euros per year, which is the expenditures on these. And our expenditures for commercial accelerators is probably in excess of 5,000 million euros per year, so 5 billion a year. So now let's get on to the industrial machines, since it's a big part of the business. And for this talk, I've broken it down into the well-established commercial applications, and in fact, I'm going to talk about them all in this order. And the developing commercial applications, and you can see from the size of the pie chart that this is sort of how you break it down. Ion implantation is, of course, well established, and both the E-beam materials processing, which we distinguish as the use of the beam for its heating properties, use of the electron beam for its heating properties. That's a very big field. And then the E-beam material radiators, where you use the secondary, you use either the chemical properties of the beam, the interaction with materials. So that's how we distinguish these two. And then radioisotope production, which Stuart talked about a little bit. It's a big field and getting bigger. Then the developing, as you saw from the growth chart, non-destructive testing and inspection machines it's been growing 9% per year for the last 10 years. And it will probably continue to grow as we have more and more concerns about terrorism and the bad use of nuclear materials. Return generators, it's growing. You're seeing more and more commercial companies getting into this business for a lot of the other things like non-destructive testing and analysis. Ion beam analysis, this is a small field that it continues to be used, but it's a, I always tell people that ion beam analysis is a QA tool, and it doesn't add value. It adds cost. So it's not something that's going to grow as fast from a commercial point of view. And then synchrotron radiation. I have included that in the commercial applications of accelerators, even though all of these synchrotrons are at national large facilities. Almost every synchrotron storage facility has a user component, a commercial user component. And there is a tremendous amount of research being done with these. And as it goes forward in the next 20 years, you're going to begin to see these dedicated machines for some of these applications. These categories, you'll find other people give talks and they use different things, and you'll see another slide I have that's different. But these 8 categories of industrial accelerators were first defined by an article I wrote for the first issue of the RAS journal, and we also used them in the book when we did the book in 2012. So. And as I said, the latest review is update of all of this is an article that's an update in the RAS 10, which I think is about to be published, and that's an update to the whole volume of RAS 4, which was industrial applications. So. Talk about how wide it is. Well, I've put the applications on beam current versus beam energy. What is it? 13 orders of magnitude in the beam current and 11 orders of magnitude in the energy. So one sees that it's not a small, concentrated field. It's very spread out. So the applications, as a result, are very spread out. So, and I mean, we're talking about these lines are for microwatts to megawatts. So some of the E-beam, for processing rare metals, some of these melting devices have megawatts of beam power. So this is my only slide about accelerators. So real quickly, this is just a brief list of the types of machines that are used in all of these applications. Electron accelerators, everything from, in fact now we're talking about from ion implantation down to the KeV region. So I mean, this is not really an accelerator anymore, but it's an accelerated particle beam up to the storage rings that are used for synchronous radiation. And then ion machines, again, ion implantation from KeV, MEV, and then cyclotrons for isotopes. They don't go up that high, but this includes also therapy, proton therapy, hadron therapy. And then the RFQ Linacs that my company manufactured, there's a lot of these being used, Linacs basically. If you look at the application, you'll see that sometimes one application uses several different types of accelerators. So it's not, again, it's not stuck that one accelerator is used for one or two applications. It crosses over. It's a very big matrix. Stuart talked about applications for energy, and I left it out because this is not yet what I call the beam business. This is still what I consider to be more in discovery science, because there's a lot of work going on these. These are large potential markets in energy, but these machines are under development, so they're not what we call the beam business, but they certainly are something that as you look forward, it's going to be a big business. And again, he went over all of these, so I'm not going to go through all of these again, but it's everything from cleaning up waste, nuclear waste, to generating energy. And in fact, a new one is actually making biofuels, cracking oil to get better quality hydrocarbons out of the ground. And again, I conclude that these are not yet industrial, but they're large research projects being conducted at national labs, which have future implications. But I can't see any value to the commercial business yet, other than components that are made for the projects for the labs. Now we'll get into the ones that are really the big ones. And I'll go through them quickly. Any one of these 8 categories I could give a 1-hour talk on, so we'll go through them all quickly. Semiconductors is the big thing in ion implantation. There are still some ion implanters are used for hardening cutting tools, in implanting nitrogen into tungsten and stuff like that, reducing friction. And then there's even several little companies that do work for using implantation for doing biomaterials for implants. It's even in ceramics and glasses, but this by far is the monster. And what we did in doing the book, we were not talking so much about the chips themselves, but the ion implanters, since it was the industrial accelerators and their applications. We follow the sales per year of ion implanters, and one sees, in fact, Mike Current, who wrote the chapter of the book on this, can actually tell you which country it was that started doing implantation for each one of these peaks. And this was as you can see, 2009 was the recession, and then now it's coming back. And this is the trend line, so one sees that it's going up. And this is the history chart of the starting in 1968, showing the rise. And in fact, this is one of the milestones when CMOS was developed. And in the last article, Mike Curran pointed out that when we did the book in 2009, 2010 was when we were writing it. It was finally published in 2012 when we finished it. I used the quote that there were between 20 and 30 passes per chip in ICs, and he tells me now that there's 50 to 80 passes through some kind of implant tool for each IC now. So it's a very big part of that. This market is mature with a few vendors. There are some specialty, small companies that are specialty companies. As you can see, the sales are cyclical for the equipment, not for the chips. But it's still growing. It's still growing. And in fact, to prove it's growing, I found a chart of the growth in millions of dollars per year for the implanters, which is this solid curve, and the growth of the worldwide GDP in billions of dollars. And you can see the correlation. And so, as the world economy grows, and as we go more and more into the electronic age, this is going to continue. My prediction is sometime that the sale of Accelerator for this may taper off when the dimensions of the chips get so small that you can't do it with particles, but then maybe we go to light to do the features. But okay, switching to one that's totally foreign to everyone here that is configured with accelerators is this electron beam materials processing. And this is basically electron guns that are used for cutting, welding, melting, and that kind of thing. And this is the oldest business in the beam business. These applications started in 1905. They're now greater than 5,000 systems worldwide. It's a mature business, but it's used in the automotive industry, construction, medical technology, aerospace. Aerospace was the first user of these e-beam machines. And these are small machines, 300 to 200 kV, with kilowatts of beam power, up to hundreds of kilowatts of beam power. And this is one of those cases where I've seen pictures of factories where they're all hands off, so it's all totally automated to e-beam well parts. And a lot of parts, you would be surprised. A lot of times it's proprietary, and then they don't tell you how they did them, but you would be absolutely shocked at the number of things in a car or a plane that have gone through one of these e-beam welders. And these things just, they have vacuum locks, they're automated, and you just shuffle stuff through there, and they weld it and send it out, and stick another in. So there's just banks and banks of. In fact, here's some of the parts that are made by that process. And you see they're showing that, for instance, with e-beam, ultra-high-density beam welding, you can actually, weld similar materials with joints up to 50 centimeters deep. So it's a big business, but it's mature, and it's not something that's there's a whole lot of vendors in it. Irradiators. Stuart covered a little bit of this. Wire cable, heat shrinkable food packaging, tires. 90% of tires are vulcanized using accelerators, inks, hydrogels, sterilization of medical products, which is the fastest growing application. And another one that's up and coming, decontamination of food and medical device packaging. This has been an application for cobalt for many, many years, but as we get more and more scared of dirty bombs, there's a push to go to e-beam sterilization and X-ray sterilization instead of using cobalt sources. And it's now greater than 1,500 of these dedicated facilities worldwide. But as Stuart said, I'll spend a little more time on this one because this is one that is one of the large and upcoming applications. Even just in the radiation processing field, one of the guys from IBA gave this a talk, and this is some of the things that he's talking about that are up and coming. It covers a wide variety of things, new materials, fiber-reinforced composites, huge amounts of plastic pipe, radiated foods, which is after 50, 60 years of being done, it's finally beginning to get some roots. And they by the way, don't call it irradiated food, it's pico-wave food. So you get away from the stigma about it. And then this one about cracking crude oil. So these are applications that are going to grow as more reliable, higher power machines become available, which we'll talk about in a minute. And again, I have the same picture he has, but I'm one of the bigger radiators. And this is, I think, the one in, for wastewater in Korea. There's been a number of projects, none in the U.S., but there's been a number of projects that are used for all of these different things. But I'll tell you, and that's part of what this workshop's all about, market acceptance has been hindered by cost and reliability of the machines. Because these are big machines, high-power machines that have to operate. You can't have downtime. 2%. They got to operate 24/7. So this is what's hindered this. So radioisotope production, again, it's the older field. This is the applications. I mean, there's isotopes that are used from cyclotrons and Linacs, PET, and SPEC are the main ones that are used. And right now, there's considerable interest, in fact, even DOE-funded projects to develop accelerators for making Moly-99 to replace the reactor production because of issues at different reactors. In fact, there's been a shortage just recently because one of the reactors was shut down. So. But as Stuart said, PET systems dominate this market. And in fact, this is just some shows you the applications. The other one that's accelerators are used for is brachytherapy, iodine 125 and plutonium-103. This shows the sales of radioisotope production machines. These radioisotopes started out being made by the laboratories on research machines as a side benefit, and finally, back in the 70s, they started doing these machines commercially, and it grew slowly until in 1999 when the reimbursement of PET procedures was put in, and by the CMSA, I guess. And so you can see what's happened since then. But right now there's about 60, no, that's 2015, about 60 units sold per year, but the top 5 manufacturers sell 50 of those. But that's not to say that they're not, they can't be a better mousetrap. So customers are always looking for the reliability and capital cost. High energy X-ray inspection. This started years ago as a site. Varian was building electrons for cancer therapy and started the division to actually use these machines for radiography of castings. And that's still a pretty big field. But then they developed the security applications to look for dirty bombs and other things like that. And what happened was the customs people found, well, you could look for bombs, but you could also do manifest verification. And so now this field is growing because not just to look for, but to look for contraband of all kinds and to verify loads. I mean, the manifest, you see this back, this is one that's actually one that was taken from in Miami at the port down there for a shipping container. And this back end had, I think it was carpets. And the manifest showed that this was a load of carpets. Guess what? It wasn't a load of carpets. And so now the many countries are putting these things in as border control for cargo, for looking for all kinds of illegal contraband. In fact, this shows the growth of these machines, and again, when we started worrying, 2001, and then poof, it's grown. But this market is dominated by two main vendors. Neutron generators. The biggest application of neutron generators now is very small ones that are used for borehole exploration. And these are built by the companies themselves. But other applications, bulk analysis, for people are actually using accelerators now to look for gold and what comes out of at the mines, to grade coal when it comes out, and to do all kinds of monitoring. Gauging and radiography, so people do neutron radiography, neutron activation analysis, trace elements, and again, security and medical are actually growing. So, as I said, this is a field that I think over the next couple of decades will grow to be much more accepted, because in fact, the number of manufacturers, smaller manufacturers of these neutron generators has tripled in the last 10 years. So it tells you that the growth is there. Again, this is an application. These are all nuclear physics applications, RBS, ERDA, all these things that are being used by companies, semiconductor companies, and others to do what I call quality procedures. Look for levels of contamination. Here's just examining art to verify the age of a painting, so you can verify if it's a forgery or an original. And but this is usually done by the tandem electrostatic and small electric accelerators made by NEC in the US and HPE in Europe. And many of these applications are still done at university labs. They do it for private companies, but there are a number of companies that have their own machines that do this for verification. But again, remember, it's a QA device. QA is an expense, not a value adding. So as it becomes more and more valuable, and if somebody finds some application for it that will add value to a product, then it would become a bigger field. Synchrotron radiation. Again, this is the oddball in that there, even though this one commercial machine has been built years ago by Oxford, there are currently no commercial vendors of synchrotron radiation light sources. FELs, maybe there will be, but this includes FELs. But the primary impact from industry is as users on these devices to do development, R&D, and some QA, but mostly R&D, and to understand more about their processes and their products. And again, it's the same thing that's true. Stuart's up here wanting to let you know that the lab will be happy to work with you in technology transfer, and all of the synchrotron light sources have industrial partners that they try to commercialize their ideas and produce new products. So, and I think my projection is that I think at some point in the future, when the applications get big enough, there will be some dedicated SRSs. Although FELs, I've been giving this talk. I first gave this talk in 1997, so I've been giving this talk 20 years, and even back then we were talking about the applications of FELs because they were such more powerful than dedicated beams. But in talking to one of the commercial guys, he said every time we come up with an application for an FEL, the laser people figure out a laser that they can develop to do the same thing, and it's cheaper. So one has to chase that. I'm not going to go over all the applications and just tell you there's a lot of work that's being done on these synchrotron light sources in a lot of different areas: semiconductors, chemical industry, and then biomedical. In lithography, nanoscale parts. So, and I mean, they can see down to the molecules, and they can actually see processes happen on the nanosecond, actually femtosecond time frame. So it's unbelievable what you can do with these, but it's not yet a commercial accelerator, which is part of this whole workshop, is that industry does well when they work with laboratories. So. All right, talk about a little bit of, sorry, I'm like late. Talk a little bit about the what I call evolutionary new commercial accelerators, superconducting Linacs and cyclotrons. They're beginning to appear. There's a medical superconducting cyclotron. There's now a company that builds superconducting Linacs commercially. The FFAG is a new accelerating device that's being developed in the UK and here that I think will eventually be a commercial accelerator for a number of applications. And again, FELs. But I said the story, that you need a broad application not possible using conventional lasers. Now, I want to put in a caveat that there's a lot of development going on by commercial companies looking at these things, but I don't know them and I can't talk about them because they're all confidential. Because no company, if they think they can use the technology to get a jump on their competitors, will actually let you talk about what they're doing until they're out in the field. And then sometimes they won't let you talk about the machines they're using, nor the number of them they have. So, and when I was trying to get the numbers out of some of these companies, I had to sign non-disclosures with them that I would use only the numbers and not associated with their company. I will put them pulled together. A pitch for the guys here, and what I think is a very close development for commercial applications is this superconducting radio frequency technology. And Bob Kephart, I'm using one of his slides from Fermilab from IR. Back at IPAC 17, and he talked about what's going on that allows this technology to suddenly be thought about as a commercial technology. The better superconductors, commercial cryo coolers, conduction cooling instead of having to flow liquid helium, new RF technology, and better electron guns. So you can make compact industrial SRF accelerators at lower cost. As I said, there is one company, Niowave, that actually has their first commercial units already built, and the folks at IARC are working on units as well. They have a partnership with the U.S. Army Corps of Engineers to look at using superconducting machines to actually be able to go over a pothole in the middle of winter and fill it in and cure it. Just by dumping the asphalt stuff in it and then using a binder that they can cure with an electron beam to do instant repairs of freeways. So, and it's certainly needed up there around Chicago in the wintertime. All right. As I finish up, I'll say a couple words, and there's other people in this room that are know more about this than I do, and I don't know if Andy's going to talk about some of this, but terahertz accelerators is one of the new and upcoming things to make accelerators much smaller. I think the initial applications may be for therapy, but who knows what's going to happen as we go forward with them. It's decades from full commercialization, but it's certainly something that has to be watched, as are laser and plasma wave field building accelerators. I don't know if they'll eventually reduce the cost, but this, again, when one looks at what the first cyclotron looked like, you never would believe that you'd have machines running 24/7 making radioisotope with it. So I'm not going to be one that says yes or no, but stay tuned. Future applications, as I said, one of the big fields that everyone here that's looking for the next few years of growth needs to look at is the top one, materials radiation. I just gave a couple examples, but in the pavement thing up at IR, this is where the growth is going to be in energy, environment, in processing, and particularly even in nanotechnology. I mean, that's takes these synchrotron radiation sources or E-beam to make some of this nanotechnology. Energy, as I said, it's tough to follow Stuart because he does such a good job describing all these applications here. But that is one of the applications that once you get reliable, high current machines that provide the power to do these applications with the reliability that they need on a commercial basis, this will be big business. Same thing with environmental. One of the guys that was on the stewardship panel with us said that he's just waiting for a disaster with all this oil exploration where they're fracking, when somebody fracks into a whole city's water supply, their wells, and you have to figure out how do you clean that water up. So it's coming. It's coming. It may take something like that to really spur it forward, but you can imagine there's a city of 150,000 people, and they have wells, and somebody fracks a well and it goes into the water. Quick conclusion, and I'm sorry I'm late, but I think without ado, one can say that industrial accelerators have an impact on all of our lives. It enables the manufacturing of products that we rely upon, protects our health, improves medical diagnostics and treatment, improves our safety and security, makes money for countries at borders. They get more income. In 2016, again, the annual market for industrial accelerators exceeded $5 billion per year. And I don't have the exact number, but I think it's probably closer to 6 or 7 billion per year. Because it's been growing for the last 10 years at 4% per year average. Some fields more than others. There's huge potential for impact in new areas, and we both covered that. And I end with a beautiful quote from the director of this laboratory. Accelerator science is a tremendously exciting period as we envision the next steps in energy, power, intensity, and brightness, powered by new concepts and technologies. As history has shown, we can anticipate that those developments motivated by discovery science will have a substantial impact across physics and society. 2011. Stuart Henning. Thank you very much. I'll be here all day, and I certainly don't mind talking one-on-one. Anybody has a lot of questions, but...
Hi, just one quick question. So you highlighted the...
Let's use the, the microphone.
Okay.
If you use the microphone, I might be able to hear you.
Okay, can you hear me now?
Yeah.
Okay, so interesting talk. So you mentioned the growth and impact of accelerators used for radioisotope production, predominantly proton beams of various energy multiple. Can you make a comment on the concept of laser-induced proton beams for isotope production, where there is some early research in that area, which become probably more cost-effective in the future?
Yeah. Most of the isotopes are neutron rays, so they're made using protons, but there are applications for short-lived radioisotopes that you like to do right in a hospital. And when you can make a machine smaller, that, hospital space is very valuable. Every square foot is $10,000 or something like that. And so if you can make a very small machine that can produce enough protons to make enough short-lived isotope, then yes, there's a place for that. And it's, as laser-driven proton machines get better and better and better, eventually that's Now, I didn't have time to talk about it, but I sometimes talk about the development cycle, and from the time when IDEO comes till the time a company started to build those machines, it's usually 30 years. So that's the kind of time frame one looks at for these new, what I call revolutionary. I talk about evolutionary concepts and then revolutionary concepts.
Thanks for the nice talk. I'd like to ask, what is the percentage of SRF accelerators being used now in the global market, and where do you think the big needs, the big immediate needs are right now to solve some of the issues we addressed as cost, reliability, compactness of the machines?
Oh, you mean for SRF? Right now it's all, I think there's prototypes commercially, and there's the work at Lab, and what SRF is going to offer you with the new developments that Bob Kephart had pointed out is more current, more power. So what you're looking for with SRF is applications that require modest energies but high power, and that's mainly irradiator type things, sterilization. Anything that uses E-beams for producing X-rays or producing chemical changes, and that's going to be where the big business is going to be. And as I said, for this environmental stuff, there's been a number of test facilities using conventional accelerator technology, but it's just too expensive and not reliable enough. When you run a machine with high power, one knows that think Stuart can tell you a little bit about Oak Ridge when they were turning it up, running that one. I mean, what's the downtime, unexpected downtime? It gets high. And you just can't do that if you're a commercial vendor. But typical therapy machine, it's totally unacceptable if the unscheduled downtime is more than about 1.5%.
Okay, with that, I think we better stop here.